Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 5.2, the addition rule and complements. Okay, so to start off with this, we have what are called disjoint events. Disjoint events are events that cannot happen at the same time, so they have no outcomes in common. What we're looking for are if two different things can happen simultaneously. For example, when rolling a die, a six-sided die, I'll just write down 1, 2, 3, 4, 5, and 6. It is not possible to roll both an even and an odd number at the same time, because those are completely separate options. Similar to that, rolling or flipping coins, you cannot both flip a heads and a tails at the same time. But there are events that are not mutually exclusive or not disjoint. For example, rolling a number less than 4 would include all of these, and rolling an odd number would include 1, 3, and 5. So that means those are two different events that can happen simultaneously. I could, at the same time, roll an odd number while also rolling a number less than 4. That means that they have events in common. What we're going to start to do here is combine multiple events at the same time. And the best way to think about that is with what we call Venn diagrams. Now, you may be familiar with a Venn diagram, but there are three different ways, or classical ways, of representing two events with a Venn diagram. So I'm going to have three boxes here. Each box is representing the sample space. So anything inside the box represents the sample space of things that could happen. All right, I'll draw one circle for each in blue. So I have a blue circle, I have a blue circle, and I have another blue circle. When you draw Venn diagrams, the most common one you may be used to is this way, with these two circles, blue and green, next to each other but also overlapping slightly. However, you could also have Venn diagrams like this, where you have two circles that are not connecting to each other. Or you could even have a Venn diagram like this, where you have one circle completely inside of another one. Each circle is representing a different event. Blue represents one event, maybe blue represents E, and F, or the green represents F. So two different events. Anything that's inside of the circle is anything that could happen with that event. So anything inside the blue circle could be represented for event E. Anything inside the green circle would represent event F. If you notice the first graph, there is some overlap there. That means they do share some events in common. Whereas the second graph, they do not share any events in common. This would represent two events that are disjoint from one another, because they cannot happen at the same time. The third graph is kind of rare. This is what we sometimes call a subset, where one event is completely inside of another one. Much less common, you tend to see one of these first two. That second one is where they're disjoint. That first one, though, is where they're not disjoint. If they are disjoint, it's a lot easier to find the probability of those two events. The reason being, when we find the probability, all we need to do is think about it as if we were to shade everything inside of blue and then shade everything inside of green. And then all we need to do to put those together is to add them. So that leads us to our first formula. If you have disjoint events, if you're trying to find the probability of either event happening, either E or F, that's what OR means in this context, one event or the other, or both, all we need to do is add the two together. So probability of E plus the probability of F. Nice and easy. For example, probability of rolling a 2 or a 4 on a six-sided die, well, that's 1 out of 6 for a 2. That's also 1 out of 6 for a 4. So that's 2 out of 6 for either a 2 or a 4. Nice and easy. However, we have what is called the general addition rule, which is the one that I highly recommend getting more familiar with. I'm also going to do most problems using the general addition rule, because this will apply to both disjoint events and non-disjoint events. If you notice, if I were to try to do that same process I did with disjoint, if I did that with the first graph up here, I would take all the events in E, so I would shade everything in E, and then I would also shade everything in F. like so. Well, if you notice what happened there, when I shaded everything in E and F, I actually had everything in this overlap here get shaded twice. It got shaded both by blue and also by green. That's problematic. That means I had outcomes that were counted multiple times, which we don't want to happen. In order to adjust for that, what we end up actually doing is instead taking out the probability of both of them happening, which is that middle value there, the center piece there. If you take out the probability of both of them happening at the same time, that means you're taking out the one instance of the values being double counted. So you're taking out that middle overlap there. You're making sure nothing gets overlapped. So instead, if I erase this carefully, okay. So instead, I would have all of E shaded, and then I'd also have all of F, and only shade F without having that overlap shaded again. That way, that overlap is only shaded one time. That is what is happening with that general addition rule. Now, the reason that we're going to use that for everything and not have two different formulas is because it's a lot easier to have one, and also because if you have a disjoint formula or if you have a disjoint situation, that means the probability of them both happening is 0, because this part is supposed to be the overlap. And in a disjoint graph, there is no overlap. So that means that that probability ends up being 0. All right, now this may sound confusing at first, but we're going to do a lot of examples of these to help you with this. To start off with, we have suppose chips are randomly selected out of a bag. Each chip is labeled 0 through 9. So note that 0 through 9 is 10 numbers. It's not 9 numbers, it's 10 numbers. You can count them if you want to. Let E represent the, choose the number less than or equal to 2. So E is a number is less than or equal to 2. And F is going to represent, choose a number greater than or equal to 8. So X is a number greater than or equal to 8. What we're going to do is we're going to compute the probability of E or F. To start with this, I'm going to write down the formula for that. So probability of E plus the probability of F minus the probability of both of them. I always write down the formula first before evaluating what these are. So I'll say that one first. Well, if I calculate these, the probability of E is a number less than or equal to 2. If I count all of those, the numbers that are less than or equal to 2 are 0, 1, and 2. That is 3 outcomes, so 3 out of the possible 10 numbers. Likewise for F, F is a number greater than or equal to 8, so that's 8 and 9. Therefore, there are 2 outcomes out of 10 that are greater than or equal to 8. Then we subtract the probability of both of them happening. So then my question is, are there any values between 0 and 9 that are simultaneously less than or equal to 2 while also being greater than or equal to 8? That's what AND is going to mean. They have both of those qualities. Even from what I shaded, 0 through 2 and 8 and 9, there's no overlapping outcomes there. Nothing was counted twice. So there are 0 outcomes out of 10 that share those, because these are disjoint. Therefore, when I add and subtract appropriately, 3/10 plus 2/10 gives me 5/10 overall. So 5 out of 10. That's it. That's what we do for OR probability. Now, I will say that OR is going to be kind of hard for people to notice at first, because that word there that we even have in bold, OR, that is very often a word that when people read things, they skip over because it's such a small word, it just links to some other things. But or is going to be an incredibly important word in probability, and is also going to be another one. In both of these ones, they give us directly that we want probability of E or F, but some other ones may not do that. You want to look for the word or something that implies the word or. We'll see a few of those. The next example uses the same situation. Suppose chips are randomly selected, and we have 0 through 9 again. However, E is now different. E is now odd number. So E is now odd. And F is that the number is less than or equal to 4. So now we're going to find the probability of E or F, which again I'm going to write down the original formula for. So E plus the probability of F minus the probability of E and F. Well, E, choosing an odd number, if we look at all those, there's 1 is odd, 3 is odd, 5 is odd, 7 is odd, and 9 is odd. That's 1, 2, 3, 4, 5 numbers, so the probability of E is 5 out of 10. Probability of F, I will circle in green. Probability of F is at a less than or equal to 4, so that would be the numbers 0, 1, 2, 3, and 4. I have circled 5 numbers, so the probability of less than or equal to 4 is 5 out of 10. Now we consider how many numbers are simultaneously odd while also being less than or equal to 4. Well, looking at how I highlighted and shaded, I noticed that there are 2 numbers that share both of these. There's the number 1 and the number 3. 1 and 3 are both odd while also being less than or equal to 4. So there are 2 numbers that satisfy both qualities out of 10. Overall, that means we have 8/10. And that would be my answer there. Remember that for both of these, you can also represent them as decimals if you want to instead. Just, I recommend not simplify your fractions. Since there were some outcomes in common here, that means that these were not disjoint, by the way. All right. So that's those first 2 examples. Now we have a couple more. We're on page 5 right here. I think we end on page 7. So this section is going to be a little bit longer. Suppose a standard 6-sided die is rolled. Find the probability that a number rolled is an even number or a number less than or equal to 3. So even number, I'll call that E. A number less than or equal to 3, I will call that F. Note the word linking these 2 different events is the word or. That's the important one. That's the key one. That's what tells you what kind of probability we're looking for. Since we have or, that means we're doing the probability of E or F. So we have our formula yet again. E plus the probability of F minus the probability of E and F. All right. Well, the probability of E is an even number. We have on a standard 6-sided die, we have 0, 1, 2, 3, 4, 5, 6. That's the sample space. An even number, there's the numbers 0, 0 is even, 2, 4, and, oh, not 0. 0 is not on the 6-sided die, sorry. 2, 4, or 6. So that would be 3 out of 6 outcomes. The probability of F is a number less than or equal to 3. Well, those are those ones. So that's also 3 out of 6. And if you notice when I did that, there are some outcomes that share both of those. There's the number 2. 2 is both even while also being less than or equal to 3. So that's 1 out of 6. That gives us an overall answer. 3 plus 3 is 6, plus 1 is 5, or minus 1 is 5, so 5 out of 6. Sorry, I ran a little bit out of room there. So 5 out of 6 is our answer there. Okay. You can also note by how I selected things and labeled things, there are some values that were not used. For example, the number 5 is neither odd nor less than or equal to 3. So it should not be a 100% chance. If I were to just do 3 out of 6 plus 3 out of 6, I would get 6 out of 6 or 100% chance. But there are some outcomes that don't fall in line with this. So that should not make any sense. Moving on, we have a guidance counselor at a middle school collected information regarding the employment status of married couples within his school district. So we have this two-way table or contingency table, as is called in 4.4. First, the probability that both spouses work. All right, well, both spouses, we scroll over, we have 1,149 out of the 1,700. So, probability that they both work is 1,149 out of 1,700. Next, what is the probability the couple has one child under the age of 18? All right, so the vertical columns are the number of children under the age of 18. So we want one child, so that is 353. So probability of one under 18, something like that, would be 353 out of 1,700. And thirdly, the probability the couple has two or more children under 18. Just like before, two or more is a vertical column, so we have 559. So that's 559 out of 1,700. So far, so good. You can also see at this point, this is why I suggest not to simplify fractions. It's so much easier to compare these three answers to each other when they're under the same, or when they're over the same denominator. All right. Next, we have what is the probability the couple has no children and only the husband works. So we want to make sure both of those situations are met. Probability the couple has no children and only the husband works. Looking up here, we have no children, so that's this column, and only the husband works. We have these 172 individuals. Those are the only 172 individuals or situations that have both those qualities. So we have probability of no children and H works to be 172 out of 1,700. That'd be my answer there. And lastly, the probability the couple has no, we have two more, sorry. Probability the couple has no children or only the husband works. Notice that word there. Again, it's very innocuous. People skip over it. Or. All right, so probability of no children and, or actually, sorry, or H works. Well, what we're going to do that is the probability of no children plus the probability that the husband works minus the probability of no children and the husband works. Well, the probability of no children, we go back up to the table. We have no children to be 788 out of 1,700. And we have husbands working, we have 425. So 788 and 425. 788 out of 1,700 and 425 out of 1,700. Then we need to find the probability of no children and the husband works. Well, we just did that. We just did 172 out of 1,700. Therefore, we should be able to add and subtract appropriately and find our overall value. I'm just going to add and subtract the tops, so 788 plus 425 minus 172. And we get 1041 out of 1,700. So that's everything that we need there. Last question. Would it be unusual to select a couple where only the husband or where only the wife works? Sorry. Would it be unusual to select a couple where only the wife works? Well, we need to find the probability where only the wife works, and we have that as 126 out of 1700. So we have that the probability that wife works, or only the wife works, as 126, I think it was. 126 out of 1700. Now, to determine if something is unusual, if you remember, we need to compare to 5%. We need to see if this is less than 0.05. So let's find what this value is. 126 out of 1700. That gives us 0.074. Or I'll just keep it as 2 decimals, 0.07. 0.07 is greater than 0.05, so no, this is not unusual. It would have to be less than 5% to be considered unusual. All right, that's it for that situation. Only a couple that were combining some probabilities there. Next, we have on the next page a printout for a deck of cards. Now, we'll be using some questions with decks of cards, so this is going to be a nice printout to understand what's going on here. But there are some things to help you if you have not seen decks of cards before. First, there are 4 suits in decks of cards. The 4 suits we have are clubs, spades, hearts, and diamonds. You can see those on the symbols there. The club looks like a 3-leafed clover. The spade looks like it's supposed to be, I think, a spearhead. The heart is a heart, and the diamond is a diamond. Each card, or each set, has 13 cards in it. The number's ace, which takes the place of number 1, up to king. So ace through 10, and then 3 face cards being jack, queen, king. These are called face cards because if you look at them, they have faces on them. So jack, queen, and king. There are 2 colors, if you also notice. The top 2, clubs and spades, these are black. And then hearts and diamonds are red. Lastly, as you can also see, because there are 4 sets, and each set has the same numbers, there are also 4 of each card. So there are 4 4s, there are 4 5s, there are 4 6s, one of them in each set. That's basically the basics of decks of cards. You won't see them too much on your homework, but we will use them because they're very good for probability cases. Nice and easy to work with. All right. Overall, with the deck of 52 cards, we're going to answer some questions. So consider drawing a card from a deck of 52 cards. What is the probability of pulling out, or what is the probability of selecting a face card? So the probability of selecting a face card when selecting a card from a deck of 52. Well, the probability of the face card should be how many face cards out of the total 52 cards. If you notice, the face cards are these ones here, the ones that have faces on them. There's 3 for each set, making overall 12. So that's 12 out of 52. Next, we have the probability of drawing either a heart or drawing a club. So we'll say that as probability of heart or club. To do that, we're going to need to find the probability of drawing a heart plus the probability of drawing a club minus the probability of drawing both of those at the same time. So drawing a card that is both simultaneously a heart while also being a club. Looking at my deck of cards, sorry for the scrolling. The hearts are these 13 cards here, so that's 13 out of 52. And the clubs are these 13 cards here, so that's another 13 out of 52. Then we need to consider if there were any cards that I shaded twice. And looking at how I highlighted, I don't see any cards that I shaded twice. Therefore, we would say that this probability would be set up as 13 out of 52 cards for hearts. There's 13 out of 52 cards of clubs rather, minus 0 cards out of 52 that are both of those. These would be considered disjoint, and if I add these together, I get 26 out of 52, or half. A few more. How about we're going to set up each of these, the probability of a 2 or a 3 from a deck of cards. So 2 or a 3. Then we're also going to do probability of an ace or a heart. The other benefit is that it's a lot easier to shorthand what each of these mean. So A for ace, H for heart. And then probability of selecting a face card or a diamond from a deck of cards. So all these are or situations, so that means we're going to follow the same formulas. So the first one's going to be probability of 2 plus the probability of 3 minus the probability of both of them. Second one's going to be probability of ace plus the probability of heart minus the probability of both of them. And last one's going to be probability of face. Whoop, face, not H. Plus the probability of a diamond minus the probability of both of them. Alright, if you haven't already, I recommend pausing the video and seeing if you can solve each of these on your own. Okay. So for 2 or 3, I look up at my list of cards, and I see for 2s and 3s, I see that there are these 4 2s here, and for the 3s, I see these 4 3s. When I shaded, I did not see anything in common between the two, so there is no overlap. Overall, that means that they're disjoint again, so it's 4 out of 52 plus 4 out of 52 minus 0 out of 52 cards, being both of them, gives me 8 out of 52. All right. Next one is ace or hearts. So ace are these 4 cards right here. So these are my 4 aces. And then my hearts, I have this line of 13 hearts. In this case, there was a card that I did overlap. This ace of hearts right here was selected twice, both as an ace and also as a heart. That's only one card though, so I am going to have to subtract out 1 out of 52 as the overlap. There's one card that is both of these cards in common, or both these qualities in common. So therefore we have 52, or 4 out of 52 aces, 13 out of 52 hearts. You'll notice 4 and 13 are very common numbers to use here. Minus the one card out of the 52 cards that shares both those qualities. That gives us 4 plus 13 is 17, minus 1 is 16 out of 52. Lastly, a face card or a diamond card. Alright, so first, a face card. Face card, if you remember, I shaded these earlier. The face card are these ones here that have faces. There's 12 of those. Then, it then said, or a diamond. Diamond is this row right here, these 13 diamonds. Overall then, that means that there are 3 cards right here, the Jack, Queen, and King of diamonds, that are both face cards while also being diamonds. So it means there's 3 out of 52 cards that share both qualities. Therefore, we have here that for face cards, we have 12 out of 52 face cards, plus 13 out of 52 diamonds, and we notice that there are 3 cards that are both face cards and also diamonds. That gives us an overall probability of 12 plus 13, that's 25, minus 3 gives us an overall 22 out of 52. All right, so hopefully that's a nice graphic that can help you understand how OR is working, because you can see them right there in front of you, even if you're not as familiar with decks of cards. Again, we're going to use decks of cards a little bit in some examples moving forward, so remember where that graphic is on page 6 in case you are not familiar with decks of cards. Before we finish off, though, we have one last page here, page 7, and page 7 is going to introduce a new concept that is going to be one of the most important concepts from all of Chapter 5, and that is the concept of a complement. A complement is another way of calculating typically probabilities, really. It allows us to look at probabilities by really addressing the problem by looking outside the box. It's one of those kinds of situations. The complement is where you're looking at all outcomes in the situation that are not included in the event. So the opposite. For example, drawing a face card from a deck of cards, the opposite would be drawing not a face card from a deck of cards. The word not is a good way of thinking about what a complement is. Now, the reason we talk about complements is because sometimes complements make it easier to approach specific problems. As an example, there was one earlier that we could have done as a complement and considered it a little bit of a different way. Let's scroll up here. It was a little while ago. Here it was. So we had supposed chips are randomly selected from 0 through 9, and we looked at doing a number that is odd or a number that is equal to 4, or less than or equal to 4. What we could have done instead was considered all the numbers that don't satisfy this, so that are neither odd nor less than or equal to 4. What we get are the numbers 6 and 8. Those two numbers are neither odd nor less than or equal to 4. What I could then do is say, well, those are the numbers that don't work. That means all the rest do. So I could instead say, take all 10 out of 10 numbers, take out the two numbers that don't satisfy this, and what we are left with is the answer we got before. That is what we call a complement. That's where you look at the opposite of your intended event in order to solve for the event that you want. That sometimes can make problems a lot easier than they would otherwise be. We have a couple examples here to demonstrate that. I will also say, though, that the formula, if you notice, is 1 minus probability of E. The reason that's helpful is because 1 you can represent as any fraction. 1 can be 2 out of 2. 1 could be 10 out of 10. 1 could be 52 out of 52. So 1 can be represented as any fraction you need, which makes subtracting fractions very easy. Okay. Now, an example of that. We have the following data represents the number of units in a random sampling of U.S. apartment complexes. First, we're going to find the probability that a complex has 4 or more units. So a probability of 4 or more. Well, notice that it says 4 or more. That implies that we're going to be adding things together. So what we could do is take all the values that are 4 or more, which is 183, 230, 204, 123, and 156. We could add all those together. So we get 183 plus 230 plus 204 plus 123 plus 156. What we get is 896. So I can answer that as 896 out of, if I add all these up, I will just say that this totals up to 1,000, which it does. Now, that's one way I could have done it. That's a direct way. Alternatively, I could have done that in a different way. I could have instead done this using a complement. I could do 1 minus all the ones that are not less than, or that are not 4 or more. So that would be less than 4. That would include 5, 11, and 88. So I could do 5 plus 11 plus 88. That gives me 104. So 1 minus 104 out of 1,000. That's the same thing as 1,000 minus 104. So 1,000 minus 104. There are some typos there. 1,000 minus 104 gives me 896 again. So 896 out of 1,000 yet again. That arguably was a little bit easier. It only involved adding a few numbers, 5, 11, and 88, which you could have done in your head, depending. But even if you didn't do that in your head, that took less key clicks, I guess, in your calculator than those 5 numbers did that were all 3 digits. So that would be an instance where complements can save you a little bit of time. In this case, I'd say either one is viable and one isn't necessarily better than the other, although I prefer complements in that case. Now, as a second example, this one can be a lot more straightforward. What is the probability the complex has fewer than 8? Okay, well, the numbers that are fewer than 8 would be all of these, because that would be 1 through 7. Or, instead of adding all those up and putting that out of 1,000, what I could instead do is just take out the complement, the opposite of this. I could find the probability of fewer than 8 by doing 1 minus 156 out of 1,000, otherwise known as 1,000 out of 1,000 minus 156 out of 1,000. If you do that in your calculator, that should give you 844 out of 1,000. That would be an instance where complements definitely are preferred. It's a lot faster to find that. You don't necessarily need to show all your work there like I did. I just wanted to show every single step. I would probably at least show this bit something. But either way you do it, you would want to show where you got your values. And this takes much less time than adding up those other 7 numbers together. All right, part C. We have what is the probability the complex has 4 or 5 units? Notice that word or there. Or means we add. So probability of 4 or 5. We do note that these are disjoint, so all we're really doing is the probability of 4 plus the probability of 5. 4 and 5 are 183 and 230 respectively. So 183 out of 1,000 plus 230 out of 1,000. If you put that into your calculator, that should give you 413 out of 1,000. That one, complements aren't necessary. You could do this by simply taking away the numbers that didn't work, but that would be the other 6. In this case, doing it more directly is better than doing a complement. I'm not saying complements are always better, it's just something to keep in mind or consider if a problem looks like it'll take too much time. We'll also have some instances in the next chapter where complements are almost required in order to solve some really complicated ones. Last question here. What is the probability that a complex has more than 1 unit? All right, well, more than 1 would be all of these together. Or alternatively, we could just consider the one value that would not be included, which is 5, and take that from 1,000. You can probably do that in your head, but I'm going to write it down anyway. Probability of more than 1 would be 1,000 out of 1,000, or 1, minus the only values that don't work, which would be the 5 out of 1,000. That would be how many have 1 unit. 1,000 minus 5 is 995 out of 1,000. In that case, complements are definitely preferred to solve that problem. You can probably do that without a calculator at all. That's how much preferred it is. With that said, that's everything in section 5.2. You should be able to go through and try your hand at the homework for section 5.2, which I recommend doing before moving on into section 5.3. If you have any questions, feel free to put them into the comments below or ask your instructor directly. But with that said, I hope you have a nice day.